Hello everybody, I'm Syed on Maths Online. Today's topic is derivation of one-dimensional wave equation. Now to solve the derivation of one-dimensional wave equation, we'll try to consider a flexible string, maybe a string of this form, right, in such a way that you will be able to form the waves. So you can see that you are taking a string in such a way that you are able to form the waves in this form. So what you are doing is you are taking this string and you are just trying to tie the string at one end of the wall. The other end of this string is tied to the other end of the wall. So if this is fixed at one end, what you are doing is from the other end you are just giving a jerk. If the jerk is given to this string, what happens is the waves will be created. So waves of this form will be created. You can see that the waves of this form will be created. So for that, what type of string that we are taking? We are taking a string, this string, whose tension is uniform throughout. So you are taking the tension, say tension T is uniform throughout. This is what we are taking. The tension T is uniform throughout. And the second thing that we are doing over here is the effect of gravity, because if the string is hanging, so gravity will be acting on the string. Because the tension of the string is too large, therefore we'll try to ignore the effect of gravity. And while you're giving a jerk to the string, the string will move in such a way that the small transverse vibrations are obtained. So you have to give a jerk in such a way that the waves that are formed should be small in nature, of this type. Alright, so this type of waves have to be created when you give a jerk. So at one end of the string is fixed, from the other end, from here, you are just giving a jerk. You are just shaking it from here. So these waves are being created. Alright, so I have just written this in the form of a statement. If you try to see here, so we are considering a flexible string tightly stretched between two fixed points at a distance of L apart. So the distance that we are taking, so if it is fixed from this end here, the total distance between this is L. So that is what we are taking. The distance from one end to the other end of the string is L. So we are taking a string tightly stretched between two fixed points at distance L apart. Then we are taking mass per unit length of the string to be rho, which represents the density. And what are the assumptions that we are taking over here? The first assumption is that the tension T of the string is same throughout. As I just shown you, the tension is taken the same throughout. That's the first assumption that we are making. Coming to the second assumption, as I told you, the effect of gravity is ignored due to the large tension of the string. The third assumption that we are doing, just now I have shown you, the motion of the string is in such a way that small transverse vibrations are taken place. So let me take along the coordinate axis. This is x and this is the coordinate axis that we have, and we are considering the wave. So only one part of the wave. So this is your wave over here, and I am taking two points, say point A, and this point A on the string is at a distance of x from the origin. Alright, let me take another point B very close to A. Alright, now this point B is at a distance, this distance is already x, and this distance which is there is delta x, a small distance. So the total distance from the origin to the point B will be how much? X plus delta x. That's the distance we have. It is x plus delta x. Now because this is a string over here, the tension will be acting. So suppose if I am taking the tension as T1 in this direction, T1 is the tension, and here if I draw a tangent, this is another the tension at the point B. If I take the tension to be equals to T2, and suppose if I just drop a perpendicular to the y-axis over here, then the angle that is making over here this angle will be alpha. Alright, so the horizontal component angle is alpha. Similarly, if I just try to draw a perpendicular from here, so this angle will be nothing but beta. That is the angle beta that I am taking. So now this is the wave that we are having along the x and y direction we are considering. So we are just taking a small element AB and we are trying to study the characteristic of this string in the small length AB. So what I am taking over here is I am taking T1 be the tension of the string, be the tension of the string, T1 be the tension of the string at the point A, and T2 the same thing, right? T2 be the tension of the string, T2 be the tension of the string at the point B. I'm just writing this statement so that you can just make notes of this. Now as the so this motion is along the vertical direction, there is no motion along the horizontal direction. Therefore the horizontal component will be, so if you write down the horizontal component, the horizontal components, this T1 and T2, because there is no motion along the horizontal direction, this T1 and T2, the horizontal component must cancel each other. They will cancel each other. So which means that you have the horizontal component along this T1. So along T1 the horizontal component will be T1 cos of, what is the angle at T1? The angle is alpha. So it is T1 cos of alpha. That will be equals to, at the point T2, the tension T2, you can see at the point B the angle is beta. So it is T2 cos of beta. Because it cancels out, we can take the tension to be equals to, say, T, where this alpha and beta that I have taken, where this alpha and beta are the angles made by, T1 and T2 with the horizontal, this represents your horizontal component. Now coming to the vertical component. So the vertical component once again at the point A and B. So let us write down the vertical component. Vertical component of tensions are, suppose you take at the point A, vertical component will be T1 sine of alpha, and at the point B it will be T2 sine of beta. So it will be T1 sine of alpha and it will be T2 sine of beta. But the question is whether both the components are positive or they are negative. Try to observe this T1 which is in the downward direction. Because it is in the downward direction, you can write down this vertical component to be negative. So it is minus T1 sine of alpha and T2 sine of beta. If that is the case, then what will be the resultant force? The resultant force acting vertically upwards. So what will be the resultant force which is acting vertically in the upward direction? It will just be the sum of these two values. It is minus T1 sine alpha plus T2 sine of beta. that will be the sum. Or I can just write down first the positive value, it is T2 sine of beta, then the negative value minus T1 sine of alpha. So that will be your vertical component. Now using the Newton's second law, let us apply the Newton's second law. The Newton's second law of motion. Because we are considering the motion of the string, therefore we are using the Newton's second law of motion. So Newton's second law of motion, we know it is force F is equals to, it is mass into acceleration. Mass is m into the acceleration is a. So what is the force? The resultant force we have taken it as, it is T2 sine of beta minus T1 sine of alpha. So this is your resultant force, that is equals to mass. Mass is the formula that you have for mass is nothing but it is density into volume. That is what we have. So we know it is density into what is the, we are studying only between the point A and B. Between the point A and B, what is the distance that you are having? Delta x. So therefore it is rho into delta x. So we will be getting the mass to be equals to rho into delta x, or rho delta x. And the acceleration can be written as dou square u by dou t square. That will be the acceleration. If that is the case, we can just try to simplify this one. So to simplify, let us try to divide the entire equation by t. Suppose if I divide this by t, so in that case I'll be getting T2 by t into sine of beta minus T1 by t into sine of alpha. That will be equals to rho by t delta x into dou square u by dou t square. So just dividing throughout by t, we have got this expression. Now if you try to bring about the relationship, we have got this relation here. It's T1 cos of alpha is equals to T2 cos of beta is equals to t. So from here I need to get this value, that means T2 by t and T1 by t. So let us try to take the first equation that we have over here. It is T1 cos of alpha will be equals to what? Will be equals to t. So you want T1 by t over here. So I'll take this t on this side. It becomes T1 as it is, cross multiply divided by t is equals to this cos of alpha you can take on the other side, becomes 1 by cos of alpha. So you can write here T1 by t to be equals to how much? Cos of alpha. Just taking this first relation, T1 cos of alpha is equals to t. We have one more result, T2 cos of beta. So let us take that value also. So T2 cos of beta, its value is equals to t. Alright, so this will be equals to again T2 cross multiply t on the other side, is T2 by t. So T2 by t will be equals to cross multiply this cos of beta on the other side, 1 by cos of beta. Now if you try to plug in these two values back over here, T2 by t, you have got T2 by t to be equals to 1 by cos of beta. So it is 1 by cos of beta into sine of beta minus T1 by t is 1 by cos of alpha. So it is 1 by cos of alpha into sine of alpha is equals to this value as it is, rho by t into delta x dou square u by dou t square. Now this is nothing but sine by cos, so sine by cos will be tan, so tan of beta, minus this is also sine by cos will be tan, so tan of alpha. That is equals to, it is rho by t into delta x into dou square u by dou t square. So this tan represents your slope. Alright, so this tan of alpha and tan of beta represents the slope. So the tan of beta represents slope at what point? Beta is over here. So beta is at the point B, the angle made is beta. So this point B is at what distance? X plus delta x. And at the point A, it represents the angle alpha. So at what distance? At the distance x. So now if I write down this tan of alpha value, tan alpha, because it is slope is always represented in the form of dou u by dou x. And it is at what distance? Alpha is at a distance of x. Then you have tan of beta. So tan of beta, again that can be represented as dou u by dou x, and angle beta is made at a distance of x plus delta x. Now these two values you can substitute back over here in this particular equation. So if you want, you can take this as say equation number 1. So your equation number 1 implies tan beta, you can substitute dou u by dou x at the point x plus delta x, minus tan alpha is dou u by dou x at the point x is equals to, it is rho by t into delta x, it is dou square u by dou t square. Suppose if I take this delta x on the other side, you can rewrite this as dou u by dou x, x plus delta x, minus dou u by dou x at x whole divided by delta x. That is nothing but this is rho divided by t as it is. Delta x is already taken on the other side. You are left out with dou square u by dou t square. Now suppose if I apply the limit delta x tends to 0, so you will be getting, so as delta x tends to 0, so limit as delta x tends to 0, you have dou u by dou x at x plus delta x, minus dou u by dou x at x whole divided by delta x will be equals to, right, here you don't have delta x value, so you can just write it as rho by t into dou square u by dou t square. Now this expression that you have, this represents the basic differentiation formula. So this represents your dou by, because dou x is there, dou by dou x of, what is this value you are having here? Dou u by dou x, so dou u by dou x. So it becomes dou u by dou x. So this is the basic differentiation formula. So dou by dou x of dou u by dou x you got is equals to, here you have rho by t into dou square u by dou t square. This dou by dou x of dou u by dou x is nothing but dou square u by dou x square is equals to, it is rho by t times of dou square u by dou t square. Now suppose if we cross multiply this t and rho on the other side, becomes t comes in the numerator divided by rho into, this is dou square u by dou x square is equals to, you will be left out with dou square u by dou t square. Suppose if I replace this value of t by rho, right, by say c square, so we'll be getting c square dou square u by dou x square will be equals to dou square u by dou t square. So where I have taken the value of t by rho, which is a constant, to be equals to c square. Or if I try to rewrite this one, it becomes dou square u by dou t square is equals to this one, c square into dou square u by dou x square. So this equation represents your one-dimensional wave equation. Or you can even write down this in the formula, because u is being differentiated with respect to t partially twice, so you can write this as utt is equals to c square times of, since u is being differentiated with respect to x twice, so you can write it as uxx. So this represents your one-dimensional wave equation, is one-dimensional wave equation. That proves the result. Thank you.